To understand what Dijkstra's algorithm is and how it works, let's start with a scenario. Let's imagine that we have a variety of different towns scattered in different locations. Some of those towns are connected to the other towns with roads, such as we could travel along the road from one town to another. Not all roads have the same travel time though. One road might take 3 minutes to travel through, while the other might take 4 minutes. And our question is this: what's the fastest way to get from town A to town B? This is a specific example of a more general problem in graph theory, where we have vertices, in this case are towns, that are connected by the edges, in this case are roads. Together, the vertices and edges form a graph, and in particular, this graph is a weighted graph because each edge has some value or weight to indicate how costly it is to travel along that edge, measured in either distance or time. And with this graph, we like to determine the shortest path from one vertex to another. So, how does Dijkstra's algorithm allow us to do this? Ultimately, we need to figure out how many minutes it will take to get to town B. In doing so, though, it might be useful to figure out how many minutes it would take to get to other towns too. So, ideally, we'd want to label each town with a number representing the shortest time required to get there. But of course, we don't know that information yet. So instead, we label each town with the shortest time we have found so far to get to that town before we've started the algorithm. We don't have any known way of getting to the town, so we label all of them with the infinity. The only town that we can label correctly is our source, town A, which we can easily label as we are starting from there, and it takes 0 minutes to get to this town. Once we have found the shortest path to a town, let's call that town explored. For all the other towns, we'll consider them unexplored. We don't know yet what the shortest path to them is. So, what we can do next is Dijkstra's algorithm. Dijkstra's algorithm repeats a two-step process. First, we update our estimates, and second, we choose the next vertex.
So let's start with the first step, updating our estimates. We know we can get from town A in 0 minutes, and because we can get from town A to town C in 3 minutes, we know we can get to town C in 3 minutes. That's much better than our current estimate of infinity, so we will update our estimate to be 3. And we can do something similar for town F. We can get there in 2 minutes, so we will update our estimate after we have considered all possibilities, roads connected to town A. We are done with the step. And now, next step is choosing which town to explore the next. And the rule is quite simple. The town we will explore will be the unexplored town with the smallest estimate. In other words, the next town we will explore should be among the unexplored town, and the one we know we can get to quickest in this case will be town F. We can get there in 2 minutes, and now the two-part process of Dijkstra's algorithm repeats. We first update our estimate by looking at the towns connected to town F. It takes 5 minutes to get from town F to town G. So, if we can get to town F in 2 minutes, we can get there to town G in 7 minutes. The sum of those two values, likewise, we get town B in 8 minutes, and we can get to town E in 5 minutes. We can also get to town C in 4 minutes, 2 minutes to go from A to F, and then another 2 to go from F to C. But 4 minutes is actually more than what we get earlier. The current best estimate for town C, which is 3 minutes, so we don't want to update anything here. Remember, for each town we want to store our best estimate for the shortest amount of time required to get there. So let's keep going, and second part of the Dijkstra's algorithm tells us to explore the unexplored town with the smallest value, and in this case that's town C, which we can get to in just 3 minutes. And the process repeats again. Going through town C, we can get to town D in 7 minutes, and we can also get to town E in 4 minutes, 3 minutes, to town C plus 1 minute from town C to E. That is 4 minutes estimate is better than our current estimate of 5 minutes. So we will update our estimate of town E from 5 to 4. To next town to explore is town E among all the unexplored towns. It has the smallest value. Notice that each time we explore a new town, it's guaranteed that we will have found the shortest path to get to the town, since if there were some shorter paths, we would have explored that shorter path first because we prioritize exploring these smaller values, and through town E, we can get to town B in just 6 minutes, 4 minutes to town, and plus 2 minutes to town to go to E to B. So we can update our estimate for town B to be 6, which is better than the previous estimate of 8. And now the next town to visit is town B.
That's Dijkstra's algorithm for finding the shortest path in the graph. Now there are few things worth pointing out. The first is that technically our algorithm has only given us how long it will take to get from town A to town B, and hasn't actually given us which path to follow. And to reconstruct the path, we have to add a step to an algorithm. Every time we update our estimate to the town, we should also keep track of which previous town we were in to get to the destination. If we keep track of that in each of the town we progress to algorithm, then at the end we can figure out what the best path is just by following those arrows backwards to the beginning. Also, it's worth noting that this algorithm only works correctly if the weights of all the edges are non-negative, since otherwise some negative length path might result in shortest path that our algorithm wouldn't be able to find. Another thing worth thinking about is how we efficiently determine which unexplored town to visit next. We want to always pick the correct smallest estimate, so some kind of priorities given. You can see this, and that's Dijkstra's algorithm. We have to keep track of distance, as you can see previous town it said, and destination V, and for edge if we can come up with shorter part to neighboring porters, we'll update our distance and remember the previous town. Once you have explored the destination, we'll have the answer.